Frank Verstraete and I had a plan of what we wanted to do. I'll move that down a little bit. The plan is not quite as what is announced. Is not quite what is announced in the schedule. So what I will be talking about is essentially today about stuff that is related to time-dependent or other stuff at finite temperature. And tomorrow I want to talk about bringing out the RG aspect in DMRG, mainly the relationship to NRG and methods that work directly at infinite system sizes. Now, from what I learned is that, it's from what some people of you told me, is that on the one hand, that there has been a very nice presentation by Miles Steinmeier on the METS method, so I will probably omit that because I was supposed to talk about that, but you had it firsthand from the guy whose paper I was recommending to you anyways. But on the other hand, I got the message that quite a few people are not quite happy about whether they really are able to do all the manipulations on matrix product states when it gets beyond just drawing the pictures. So what I do is I will start, and that I think has this already been copied and distributed, you know, this slide. Okay, this is new from this morning. There are pages A to E, which are new, and they are right behind the literature list, which I put on page number 2. The literature list is not stuff you are required to read in any ways, because it's a lot, and I hope that sort of we will be able to make these lectures self-contained. So there will be sort of like a part 0, which I start with, which is called Some Manipulations on Matrix Product States. Basically, this is all stuff you should already have had mentioned, and probably you had, but I want to put it together so that you really have a list of the typical manipulations you can do. And then we get to the algorithms. I mean, what you have all seen already is that a one-dimensional quantum state, in fact, you can take it also to higher dimensions, but then it's not a very smart notation, is given as follows. I would have a sum over the entire computational basis, like spins, sigma 1 to sigma L. And then I have here a basis state, sigma 1 to sigma L. And my scalar prefactor C sigma 1 to sigma L, which we have in quantum mechanics, would be represented by a product of matrices, which I will call here M sigma 1 times M sigma 2, and so on and so forth, times M sigma L, where the only thing you have to watch out for is that the matrix dimensions match, like that the column dimension of this one matches the row dimension of this one, otherwise you can't multiply. And that, of course, the first one starts out as a row vector, and the last one ends as a column vector. I mean, this is for open boundary conditions, for periodic boundary conditions. The whole story would be slightly different. In between, you can do whatever you like. And what you also already have seen is that there is a graphical notation for all that, which I will briefly repeat, is that you would represent this state like this. This should be very familiar to you. And everywhere here, I put one of these matrices. And for example, here I would have the matrix M sigma I, and it would have row and column indices A and B. Then A would be here on this leg, B would be here on this one, and the physical state sigma I would be up here. So another statement which I think might be quite important to remember is, how does this notation relate to the blocks of that you have encountered in DMRG? Imagine that you have a block of, say, spins, and the length is not so important at the moment, let's call it small l. But anyways, this is described by an orthonormal system, which I will call AL. And whether this is a complete basis or not, we will ignore that for the moment. The only thing I insist on is that it's an orthonormal system. Now I add one side. I will describe its degrees of freedom by sigma L plus 1. And you build the next block, which is one side larger. So where somehow I've incorporated this side here. And this will be described by an orthonormal system AL plus 1. And the relationship to matrix product states, I now want to explain as follows. If we take the following notation that we say AL plus 1 is of course a linear combination of AL sigma L plus 1, AL sigma L plus 1, then I get of course the expansion coefficients, which I have here. And my rule for writing the matrices is simply the following, that I say I take my matrix A, or I call it M here. I will switch to a notation, I will call it M for the moment, but we'll see that we can be more specific in a second. I take the matrix M sigma L plus 1, and then this will be the row column entry AL plus 1. So it's just a rewriting of the standard quantum mechanical formula. This, of course, would hold irrespective of whether, I mean, I could expand any state like this, even if they are not performed by orthonormal systems, then it would be linear dependent, non-unique, whatever, but I could write something like this. But if I focus now on the special case where these guys are forming orthonormal systems, I get something quite important for matrix product states, namely that if I demand that these states are orthonormal, meaning that the overlap AL plus 1 prime is simply given by delta function, then I can now insert my expansion. Basically what I do is I insert a quantum mechanical 1 here in the center, AL plus 1 prime. So, and if I now use the notation I just introduced, and this is A sigma L plus 1, AL plus 1, and of course it's conjugate. I give that whole thing a star. And this is A sigma L plus 1, AL plus 1 prime. So I can simplify that if I say I take the transpose of that, and then I can take these guys to be simply a matrix multiplication. So what I end up with is sigma L plus 1, A sigma L plus 1 dagger times A sigma L plus 1, and of these guys the matrix elements AL plus 1 and AL plus 1 prime. So if you now take this formula, what you get is I, the identity matrix, is the sum over sigma, A sigma dagger, A sigma. And as you will have noticed, I have silently switched from a notation where I have a general matrix in the matrix product state which has no special properties. I have switched to a notation of A, where I mean a matrix in a matrix product state that obeys that property. And this property, which is very important, is something I call left normalized. Similarly, and you can work out that on your own, if you think about DMRG block growth, where you add a side to the left and make your block bigger. I mean, I'm sure Steve White has shown you these pictures where you have blocks with spins inserted and they grow and they shrink. And this is one that would grow from the right. And here I can also, of course, introduce these matrices M. I will call them B because you can show that from demanding orthonormalization, what immediately follows is that you have a different type of matrix on the right, which I would call I, which obey the following relationship. I, the identity, is the sum over sigma of B sigma dagger. So the dagger changes its position. And these I call coming from the right, growing from the right. I call these guys right normalized. Okay, so, and why are these guys extremely important for all practical manipulations you do in matrix product states? That actually you can see most easily from a graphical representation. Let me do the following. If I have a matrix A sigma represented graphically like this, AB, let's do AB here, then I represent the matrix A sigma star, AB, as follows. I simply sort of like turn it around. So this would be sigma AB. Then, sort of like I could represent this equation here, for example, as follows. I multiply these two matrices and I multiply, and they have the identical left index because it's the left index here and the right index of the transpose that are contracted in the matrix multiplication. So if I draw these two matrices like this, then the multiplication of the matrices just means I have sort of like a common leg here on the left. And at the same time, I'm summing also over the sigma index, which sits here. So here this would be this A, and this would be B prime, if I stay in this notation. And what comes out is simply the identity. So the simplification would be that what you then get is simply a line which corresponds just to a 1 or a delta function, which makes the two legs on the top and the bottom identical. At the same time, this would hold for these A matrices, A and A star. At the same time, the same picture holds from the right. That if I write down this expression, which is nothing but this one, where I have the rule that I contract over joint legs, but I'm sure you have seen that already. That gives me the identity again. Okay, so what we have now is that we can represent a matrix product state. We can have a sort of like a jumbled up representation where these matrices are whatever you want. This would be the generic notation. But you can also have something which I call left canonical, which is a matrix product state which is given in the same form as here, and it's all formed from these matrices A sigma 1 to sigma L, which obey this relationship. Then quite naturally I can introduce one which I will call right canonical, which is all made up from these B sigma 1 to B sigma L matrices. And what in view of DMRG and other algorithms is actually even more important in many cases is something which I would call mixed canonical, where I write a state psi by summing over all the sigmas, and the matrices are now mixed in the sense that I start from the left, say up to a side L, and then sort of like I continue by matrices in the B normal and the right normalization up to side L sigma. And to join these two guys, I mean, I can simply multiply these together, but I give myself the freedom of introducing some matrix which will often be diagonal, but need not be diagonal, which I insert here at the middle between side L and L plus 1, which I call lambda L here. Why this is very useful, it can be seen in a second, namely, first, if I can rewrite that, I can take the sum over the sigma 1 to sigma L together with the state sigma 1 to sigma L, and then sort of like the whole thing turns into a state which I call AL. On the left half of the system, which I call ALA, and from this construction here, which shows that if these matrices obey such a condition, which they do by definition, then I generate an orthonormal set. So these matrices here are orthonormal, and I can write them down explicitly, which would be sigma 1 to sigma L, A sigma 1 to A sigma L. This will be a vector if I take its component AL, and here sigma 1 to sigma L. This is just the state I'm introducing here. And similarly, I can introduce such a state on the right. So let me write this lambda L matrix element AL, AL prime. So I have a second sum here, and we have AL prime B on the right-hand side. So what you see here is you have expanded your state psi, if you have it in this notation, right away into orthonormal systems, which you can read off from this representation. And if you want to get a Schmidt decomposition, which would correspond to making these guys diagonal, you do a singular value decomposition, which generates you unitaries on the left and right, which you can absorb into the A matrix here and the B matrix here, and it will not change anything about these relationships I just mentioned. But let's ignore that for a second. So one thing which I will discuss in a second is, but not now, but just mention right here, is that in whatever notation you get your matrix product state to start with, you can bring it in either of these forms. And doing that and being able to switch freely between these different notations, because they are very useful, is one of the most important parts of being able to work with matrix product states. And actually, it's quite easy once you have seen it. But what I want to repeat first is to actually show you why it's interesting to have these guys in, for example, this form, is that I do what we like to do in quantum mechanics. We like to calculate overlaps, expectation values. So, for example, the overlap between a state phi and psi, and you have certainly seen the formulae, so this is just a repetition now, is that, say, this is the state psi, which I describe by matrix. Let's assume it's all left normalized, so these are matrices A. And the state psi will show up with its conjugate. So the conjugate is simply provided by starring it and turning the notation around. So this would be the state phi. And I call these matrices, I assume they are also left normalized, I call them A tilde. So if we now work out the formula, we see the following. What would happen? I have to sum over all the sigmas, because this is the basis we are expanding in, and then I get the conjugate coefficient of phi, which is A tilde sigma 1 to A tilde sigma L star, A sigma 1 to A sigma L. I assume you have seen that, but I think we will need these manipulations quite a bit in the following, so bear. Those who want a repetition, fine, and those who already know it perfectly, please bear with me for another few minutes, then we are done. So this is scalar, so because it's a scalar, I can transpose it just like that. Then I get a dagger here, then I resolve the dagger, which means I have to invert the order of these guys, and I get some sigma A tilde sigma L dagger to A tilde sigma L sigma 1 dagger, A sigma 1 to A sigma L. So the next thing you do is, in order to evaluate that most efficiently, I mean, this corresponds to doing all the contractions which are sitting here, these multiplications. Now you could think about, in a bad way, to contract all the matrices down here, which would be very expensive. But the worst thing is that you still have an exponentially large sum to carry out here. But the whole thing can be done much more easily if you contract like with a zipper, starting from the left, for example, which would then give you, say, sum sigma L, A sigma L tilde, brackets, sigma 1, A sigma 1 dagger, sigma 1, here's a tilde, then it continues with A sigma 2, sum sigma 2, A tilde, sigma 2, and so on and so forth. And what you see here is now you get a very simple sum of matrix multiplications of always multiplying, sort of like 1 here at the center, then you multiply it to the left, to the right, to the next sum, and so on and so forth. Okay, but you see now, I mean, when you do this efficient bracketing, you see now why, for example, this left canonical representation might be useful. First, assume you might want to calculate the overlap of psi psi. Then, of course, the A's and the A tildes would be the same. And then what you would get here is simply the relationship A sigma dagger times A sigma summed over sigma. But we already know that this is the identity. So this would collapse to the identity. And then, of course, the next one would collapse to the identity, and so on and so forth. So this whole thing would give you, without any explicit calculation, that the norm of this matrix with the state would be 1. You could also do that graphically, saying once you have done the most inner one and obtained the 1, you are in this situation. You get rid of the next one by this rule. You get rid of the next one until you are right there at the end, and then you are looking at a scalar delta function, which is just the number 1. Okie doke. So now let's look at an expectation value, because for expectation values we will realize that this mixed canonical representation could be very interesting. What would happen if you do an overlap calculation? It's the same story as here, but assume I have an operator on side L, which I sandwich between states psi. It's the same picture as here, but at side L, you sandwich the operator OL in between. I mean, this sticks out a leg sigma, this sticks out a leg sigma prime, and the operator has matrix elements O sigma sigma prime. So this is just what you have to do. But now if you assume that you have this state in exactly this form, or more or less this form, I relax that assumption even a little bit. I just say I want A sigma 1 to A sigma L minus 1. I want B sigma L plus 1 to B sigma L sigma, and I don't care at all what the form of M is on the side L. It could be left, could be right normalized, could be whatever, because if you then do the expectation value, and you use this rule from the left and that rule from the right, you can get rid of all of that until you arrive at the following expression, which I put here, where this is just a delta and this is just a delta function too. So if you wish, you could write down the final expression. OL, the expectation value, is the sum sigma L prime of our operator, which connects these two states. And then, sort of like, I have the multiplication of this matrix with the other one, both from the left and the right, and sort of like you can write that as A sigma L dagger, A sigma L prime, and then you trace the whole thing. If you write down this expression with indices, you will see this is just what you get here. The multiplication makes the one set of indices identical, and the trace makes the other set of indices identical. So, and what is therefore extremely useful is to be able at any moment to switch in matrix product states to any of these notations. And what I now have to show, or want to show, is how do you transform between matrix product states of different kinds. This is just special cases of a quite generic gauge degree of freedom in matrix product states that you can insert, of course, between any of these matrices. You can insert something which has the form x times x minus 1, so any invertible matrix of the right size so that it matches with the matrices where you insert it will do. And I will make special use of this gauge degree of freedom. So what I will do is I will simply explain how it works to go from a very generic matrix product state to a one which is left normalized. And it will be an exercise for you to think about how to do it from the right to get the E matrices, or to do something mixed canonical, but it's very obvious once you see it here. So the decisive step is the following. I have the set of matrices M on side 1, which is called M sigma 1. There are D matrices if D is the number of local degrees of freedom. And from these, I form a column vector where I arrange these matrices as M sigma 1, M sigma 2 to M sigma D. I can also do that in an index notation. But I say from this matrix is M sigma 1. And there's a special case on the first side. They are, of course, vectors. So I call that M1, A1 for row and column. I reshape these matrices into one, which I call M. And then I have a mixed index 1, sigma 1, A1. So if that were not a scalar, I would have sort of like another index here. We will get that in a second. Then I do a singular value decomposition, which I think you have encountered tons of times by now. Let me be a bit explicit here. 1 sigma 1 A1 is nothing but the sum over S1 U 1 sigma 1 S1 DS1, these are the singular values, V dagger S1 A1. And one thing you know in SVD is that U dagger U equals 1. So from U dagger U equals 1, you get some 1 sigma 1, U dagger S1 1 sigma 1, U 1 sigma 1 S1 prime is delta S1 S1 prime. And now I do a reshaping. I reshape U1 sigma 1 S1. From this I form again a set of matrices in the following way that I say this is A sigma 1 1 comma S1. It's another reshape. Basically it's always reshapes and doing SVDs. That's all you do all the time. And then from this expression here you find right away that this gives you that the sum over sigma 1, A sigma 1 dagger, A sigma 1 is the identity, which is just what we had here. So the first matrix already obeys the condition you want. So what do you do with the rest? So like these are still around from your original matrix M. I multiply all this bunch into the next one, the set M sigma 2. which is, this matrix multiplication is perfectly harmless in the sense that, of course, this multiplication will destroy any specific properties the matrix might have had, but I didn't demand any specific property anyways. So it doesn't really matter. And so the state now looks like some sigma, A sigma 1, D, V dagger, M sigma 2, M sigma 3, and so forth up to sigma. And this will be just my new M sigma 2. Okay, so what do I do to this M sigma 2? Which has indices S1, A2. I reshape that into M S1 sigma 2 A2, and now you see the same game happens again. I do an SVD, get a sum over S2, U S1 sigma 2 S2, singular values labeled by S2, and a V dagger S2 A2. So this guy will be reshaped into A sigma 2 S1 S2, and these guys I will multiply into M sigma 3, and you can show in the same way as here that A sigma 2 obeys the same property as A sigma 1. So what you get is your state now, I leave out all this, well, A sigma 1, A sigma 2, and then you get D, V dagger, N3, and so on and so forth, and you continue like that, and then you have arrived at this representation here. And similarly, coming from the right, with a simple reshaping, you get it into this form, and starting from the left and the right at the same time, you can sort of like do it until you hit each other, and then of course you have all this garbage, like these DV daggers in the center, and they will make up your lambda matrix. So, okay, we can do all that, like I can get any form. So I have spent considerable time now on that, because my claim is that if those of you who actually want to sit down and program any of these algorithms in order to make them efficient, stuff like this, and this will be really the workhorse of your algorithm, because usually what you see is that the actual algorithms are just mixing together various steps that work like that, so the major programming effort really goes into doing that. Okay, so the last statement I want to make before now moving to algorithms are two things which I will perhaps only need tomorrow. So perhaps looking at the time, I will perhaps leave the description of reduced density operators and this formalism up to tomorrow where we'll actually need it. And so from this introduction or repetition of the techniques, I will now make a jump into the original set of lecture notes to page 3 for those of you that have them with you. And we will cover the rest of page D and E early tomorrow, because we won't need it right now. Okay. So another remark is when it was copied yesterday, some page 21 went missing, so that should be around loosely in your set of lecture notes. Okay. So let's do now finite temperature in DMRG and or matrix product states. And the nice thing is that if condensed matter physicists had known a little bit about quantum information, they could have seen that it's in fact very easy, but we didn't, of course. And it turned out that the fact that you feel that simulating a pure state may be one thing, but looking at the density operator, which is of course a mixture of all pure states that can show up in a system, that might be infinitely more complicated and a very hard thing to do. And it turns out that in fact it's actually very easy due to something which in quantum information has been known, I think, There's some experts here in the audience, but I think it had at least been known since Ullmann or even earlier on in the 70s. But we didn't know about that, so, but you will see it in a second. This here at the moment. And so one thing which you have certainly also seen already is the Schmidt decomposition. Assume we have a universe which consists of A and B. It has a Hilbert space HA times HB, and the dimensions are dA and dB. Then the claim is that arbitrary state psi AB, which is a superposition of states I on A and J on B, let's assume that this is an orthonormal system, but even that wouldn't matter, it would just matter for the way how you calculate it, can be brought into the form sum alpha equals 1 to R, times some positive numbers W alpha square rooted, and then a superposition of states, but which is now pairwise. So like they are not superposed one with every other one, but only pairwise like this. And what you can say is that the number of contributions is less or equal to the minimum of dA and dB. What you also can show that if the state is normalized, then the sum of W alpha equals 1. And you can also show that the alpha A and the alpha B's are orthonormal systems. Okay, so this is only the case if psi is 1. So, but what you can also do is, and that's nice, is you can immediately read off the reduced density operator of the subsystem A by the sum of alpha W alpha, alpha A, alpha A. Simply trace out B, the alpha B's in that expression. This is nothing but the trace over B of psi AB. Okay, so, but that's all. That's all we need to do finite temperature. Because what you see here is that a pure state, well, let's enlarge that to here, that a pure state on a system AB can be turned into a mixed state by tracing out part of the system. That's an almost trivial statement, but the interesting story happens if you do the trivial inversion of that procedure, because then you arrive at something which is called purification. Where I say, can I get from a mixed state to a pure state? Because if I find a pure state representation of my mixed state at some cost, which we will see in a second, then of course I could recycle all the algorithms I have already developed for pure states. And I mean, Adrian Feigwin, for example, he has shown you time-dependent DMRG for pure states, which means once we have solved this issue here, you can do right away time-dependent DMRG for mixed state, like thermal density operators. So what I do is I will identify my subsystem A here. I will take that to be my entire system. I will take that as the physical system. And the most general mixed state on the physical system will have this form. I mean, it has just been brought into its eigenrepresentation. This is already the most general density operator you can write down with all W alphas between 0 and 1, and they sum up to 1. All the properties you already have from up here. But that means that you can read the formula backwards, and we introduce a fictitious system, which I call auxiliary system. And I make this dimension of this auxiliary system, it could be larger than A, but it's actually not necessary. I will take its dimension just to be the one of the physical system. So if this has a dimension 2 to the power L, then that will have a dimension 2 to the power L2. I can give it an arbitrary basis, which I call alpha B, but the thing which I will do is I will simply identify a physical system and auxiliary system. So if that's a spin chain, for example, well, I will make the auxiliary system yet another spin chain. So I have two spin chains all together. And if you now write the pure state on the total of the two in this form, then from tracing out the auxiliary system, you get a reduced density operator just in the form you wanted, which means that from the mixed state, rho A, which you want to simulate, sum W alpha, alpha A, you arrive at the pure state by writing psi AB is sum square root W alpha, alpha A, alpha B, and the rule is simply that you say if I want to then get back to my density matrix, I have to take the trace. So essentially it's a really trivial operation, and this is what you would call the purification. Okay, so I already mentioned that what we will do in practice is we will double our physical system. So imagine this is a spin 1/2 chain. This is now the physical one. The auxiliary one will just be, I will draw it like that, will be this thing here, another of these spin chains. But it need not even be spins, it could be hardcore bosons or whatever. There's no need to give it the same physical interpretation. I just want to replicate the structure of the Hilbert space. There's lots of degrees of freedom there. I'm doing that this way because I want to remind you of the fact that this now looks almost like a spin ladder. Well, apart from the fact that they are not really interacting. But it looks like a spin ladder, and there have been tons of simulations in DMRG of spin ladders. So actually, if that's the numerical problem you have to solve, the message is it's nothing difficult. Okay, so the problem, however, is that this formula looks nice, but the problem is in order to write down the purification, for which you can run your standard DMRG or matrix product state algorithms, unfortunately, to do that, you would have to know the W alphas and the alphas, the states, the eigenstates and the eigenvalues of the density operator. Now the problem, of course, is in a many-body problem, knowing these guys is, of course, exactly the problem. I mean, so it's not a very helpful procedure because in general you will not know these guys. So you have to find a way out, and there are important exceptions where in fact you can generate both the basis and these W alphas and therefore write down your purification. And for us, most important exception, it's not the only one, but the most important exception is simply the one where we are interested in a thermal density operator. And I will do this construction now explicitly, and it goes in two steps. First of all, you consider the infinite temperature, or beta equals 0 density operator. I will note everything now in units of beta. So here I still write beta equals 0, which is nothing but 1 of the partition function, 1 over C0, e to minus 0 times the Hamiltonian, which is nothing but 1 over the partition function times the identity operator. And of course, C0 is the trace over A of the identity operator, and this is nothing but the dimension of our Hilbert space. For example, that could be D times to the power L, if this is the local dimension. Okay, and now that can be constructed very easily by hand, so that we have something to start with. To be specific, let me take a spin chain of spin 1/2, and from 1 to L. And the first thing I know is, because it's an infinite temperature, and if I look at this 1, this factorizes. So this is tensor product of the local density operators for infinite temperature. Of course, this relationship will not in general hold for any finite beta, but for 0 it's okay. So now what I have to look at is now sort of like the purification of the identity operator just on a two-side, or DC. Here it's a two-side problem, two-state problem, so I can write it down by hand. Rho I at 0 is 1/2, and now just the projector on the two states. So this is the 1. And if you want to be very specific in the notation, you know that this is on side I. But it's very obvious that from this follows a purification psi AB at beta equals 0, which is a product state psi 0, 0, psi 1, 0, just a product of the local purifications. And the purification of this guy is very simple. I need something that upon tracing out the environment gives me just this structure here, and you can check on your own that an expression that will do is the following totally mixed state that pairs up spin-ups on the auxiliary and the physical side, and spin down on the same two sides. So basically you link these guys up here in a superposition of up, up, and down, down. Let's make a new picture here. So this is where this state here lives. An extremely important remark is that the only thing that matters here for this construction is that this state is maximally entangled, meaning it reproduces a totally mixed density operator, which is just what we want here. For example, in this case here, a better way of writing it would be the following. As follows, I do up, down, sorry, plus or minus down, up. It's very easy to see that this is also a totally mixed state, and if I trace out over these guys and pair up, up in the projector and down, down in the projector. But what you see now is that the total magnetization of this state here is 0. Either if it's plus or minus, doesn't matter. So if you have a DMRG code for the spin ladder that emerges, that conserves total magnetization, you are much more efficient than with this state, which does not conserve with quantum numbers. Here it's up, up, here it's down, down. If you take the minus, you are in the total spin 0 sector. So if you have an even better code, which does non-abelian quantum symmetries, which we usually use in my group, then this is even more efficient, because then you have two very useful quantum numbers, SC and total spin at the same time, and these calculations become much more efficient. But sort of like this is sort of like a remark on the side to start with. This other one will do as well. So now we have found our purified state. So what we now have to do is we have to bring it in the form of a matrix product state. Because you want to write your code, and for that you have to bring it in the form of a matrix product state. And let me take the state, which is a singlet up, down, minus, down, up. And what I first do is I represent that as one big site with local state dimension 4, where I take these guys to be one big state. So what then happens is the total state psi is a product state, as we have seen down here, which means that the matrices in the matrix product state, they all become scalars. A matrix product state is equivalent to a product state exactly if and only if, well, unless you have written it in a stupid way, if it's sort of like consists of scalar matrices. So what we can write is psi is the sum over sigma, and as you will see, they are all well normalized in a second. And then this a sigma a, well, here I will make that to show you that we are now here looking at these big sites where it's both the spin here and down here. But if I'm explicit here, up, up has coefficient 0 because it doesn't show up in this formula. A up, down is 1 over square root of 2. This is minus a down, up. And this guy here is down, down is also 0. So the message is that if you want to do an algorithm with a matrix product state and you start at 0 temperature, or sorry, beta equals 0, infinite temperature, you can write down a matrix product state right away. And you may think about it for a second, what would happen if you wanted to introduce a matrix A here and there. So basically that you would factorize these guys again into the two spins. Perhaps this is sort of like a small homework you could think about to see whether you understand how to work with these matrix product states. The answer will be that you will have a 1 times 2 matrix here and a 2 times 1 matrix here, and it just remains to find the entries. But it's actually not necessary, you can work with that. It only becomes a problem if your local state space dimension here is already that big that d squared becomes a huge number. And you have to think about something better. Okay, but now we are already almost done with doing finite temperature calculations. Everything that is difficult has already been done, because now we do something really profound, which you would never have thought about. It's so simple. The density operator at finite temperature, we all know what it looks like. It's 1 over c beta e to minus beta h. So, and now I write this as 1 over c beta e to minus beta h over 2 times the identity times e to minus beta h over 2. I think that's, stuff like that's all. We are done. Let me show why. This guy here is just the reduced density operator at infinite temperature up to normalization. So, now I insert my purification. This is trace over the auxiliary B of psi 0, psi 0 living on AB. I hope my notation in the notes is a bit more consistent, but I think you know what I'm talking about. E to minus beta h over 2. So the next thing you can do is to observe that this Hamiltonian, the physical Hamiltonian, of course, only acts on your physical system A. Therefore, it's not affected by the trace B and vice versa, which means I can pull out the trace, and I get C0 over C beta trace B over psi beta where psi beta is E2 minus beta half times Hamiltonian psi 0. Okay, and that's all you have to do, because this guy here we have now constructed explicitly, even writing down the A matrices in full detail. This here is a time evolution. It's an imaginary time evolution. So you just recycle the time-dependent DMRG code, which I hope you have, and then sort of like you switch your time to imaginary time. In fact, that makes the code even more stable, because while real-time evolution is a unitary, meaning that any errors you have picked up are there with you to stay, roughly speaking, this exponential will dampen out errors you have done early on in your time evolution, so it's even a bit more stable. It reminds a bit of the Wick rotation you would like to do in field theory from the real to the imaginary axis and vice versa. But I mean, this is sort of like not important. The only important thing at the moment is that this is something you can do if you have time-dependent DMRG at your fingertips. Okay. And then sort of like, I will look at calculating expectation values in a second. The one thing which we have to worry about a little bit is the normalization, which I have not talked about yet, but we will get to that in a second when I have wiped the blackboard.
Maybe we have two practical questions.
Yes.
So one.
Let me see whether I can wipe while listening to your question. Go on,
so how do you select psi of 0? Is there any good choice for this imaginary time evolution, or
psi 0 was constructed. So here, the psi 0 I constructed here explicitly with these A matrices from this. This was sort of like the purification of one bond here, and then the total state is just the product, which means the A matrices are scalars, and I just have to find their scalar entries, and I copied them from the singlet state. For practical reasons, I recommend that, because this conserves the maximum number of quantum numbers you could have in that particular problem. It's, in that sense, the choice has a practical application, but it's not free beyond these unitaries. You want a maximally entangled state. And there you can, depending on the problem, of course, make a smart or a stupid choice. That's number 2.
What's the beta of, that you can reach typically?
The beta you can reach typically. We have not really pushed this to the extreme limit in the sense, well, perhaps I should, there will be a point a bit later in this presentation, as of like when it goes about doing thermodynamics, we played with betas up to 50. But then at some point you will definitely reach a limit. I don't know whether the talk about Metz mentioned that the purification approach basically simulates 2 independent chains when you go to beta equals infinity, and then the number of states you need in the DMRG approach basically is the square of the one you would need for the pure ground state, and then it's highly inefficient. I was personally more interested in real-time evolution, and there the thing is that at high beta actually got further in time, but we did not really push it towards beta, towards 0, but there again the same problem would happen. But I would say, okay, perhaps these problems, spin-1 half chains were a bit simple. Okay, they have a complicated spin-on structure, whatever, but I would say beta equal 20, 30 should be doable always. If you ask me about beta 100, 200, I would highly doubt whether it works. But it would really depend on the problem, what the gap is, and so on and so forth. In the end, of course, the gap shows what degree of admixture you get. In some sense, you could say once your beta is larger than 1 over the gap, then probably you're getting into this factorization regime where the whole thing becomes very inefficient. So critical systems would probably be more benign here because they preserve amount of entanglement between the two chains, and a fully gapped system, which normally is the easy case, would be harder for purification. But I'll talk a little bit about that towards the end. Let me now worry about the normalization. Well, there are various ways of attacking this issue. The one thing is you could, of course, make attempts on calculating that explicitly. That's actually, I think, possible. But it's easier just to say the following, namely, a property which I definitely want to have is that at any temperature, the expectation value of the identity is 1. Now that's generally accepted, and for all beta, and then of course this number 1 would be the trace over A of the identity operating on A, rho A beta. So I write that as my trace over B of the purified state. So what I get is the trace over A and B of, well, the 1 I ignore. It's just the 1. Psi AB, psi AB. And now the complete trace over this projector gives us nothing but psi AB, AB. So the message is your purified state has the proper normalization if you keep it normalized. If you keep it normalized, it gives the expectation value of 1, and then you have not to worry about these C0 over C beta anymore. So, okay. So the density operator is properly normalized if the purified state is normalized. Okay, and that's of course what you can easily maintain in your code. Even more, if because of this exponential here, the norm will not stay at 1 and you always have to renormalize it. But if you accumulate these factors, you have in renormalizing this expression, then you just get this expression here. So monitoring the renormalization factor at each step gives you C0 over C beta or C beta over C0, depending on how you write it. And given that C0 is e to the power L, keeping track of the normalization gives you right away C beta. And one nice thing you can do, of course, is once you have this is a thermodynamic potential. From this you can, without any further ado, calculate other thermodynamic quantities if you're interested in them. Perhaps more interesting to us in thermodynamics are expectation values. O rho beta is trace A, operator on A, trace B, psi beta, and if I have not bothered about the normalization, I can put it explicitly. I mean, we have down here, normalizing by the expectation value of 1. So if you pull the trace here, what you see is this is nothing but psi beta, O psi beta, times psi beta, which means, and if you totally ignore the normalization issue because you can't be bothered at all, the standard quantum mechanical expression for an expectation value will give you the right expression. So in this purification, you can really work without ever really worrying that what you are actually doing is that you're looking at a mixed density operator. Okie doke. So let me now sort of like take this algorithm and see what you can do with it in the last 25 minutes we have. I think this will just match the fact that I have replaced METs by a repetition of the standard rules of matrix product states. So let me see what we can do. When we first played around with that, this was back in 2005, my Lens student Thomas Bartel, some of you know him. We programmed that, and we looked at thermodynamics, looked fine. We looked at expectation values of correlators like S plus, S minus, I don't know, many sides apart, and all that looked very fine. We didn't bother to publish it because the thing we were really interested in was to move to dynamical structure factors at finite temperature. I mean, if you think about people in Newton scattering, what they measure is a structure function, a structure factor. I always mixed it up what it is in English, because I think this is changed to German. But anyways, at zero temperature, there's some well-established techniques, also in DMRG, so-called dynamical DMRG. At finite temperature, it's not so clear what you can do. And the problem with many of these experiments is, nowadays, that because you want to work with high magnetic field, and it's very hard to get a very high magnetic field, so what you have to have is you have to have magnetic compounds with very weak interactions. Meaning, say, there's this rule of thumb, 1 Tesla, 1 Kelvin, so you want to have a compound that has interaction parameters that are of the order of, say, 10 Kelvin, then you're happy. So your scattering is done, and the compound is kept in something like helium temperature, means it's at 4 Kelvin, meaning that the temperature of the compound relative to its interaction strength is something like, well, beat 0.4 or something like that. So if it's much higher, of course, you don't see the quantum effects anymore. But of course, what you would like to have to see the pure quantum physics is to get temperature down to 0. But unfortunately, you won't be able to do that in these scattering experiments. So what you would like to have is a method that gives you structure functions at finite temperature. That's something experimentalists would love. And so what could you do? And that's what we tried. It's dynamical quantities at finite temperature. So the standard rule, and I'm pretty sure that, because this holds independent of temperature, Adrian has already shown to you, the expectation value of this guy here at some temperature beta is nothing but the trace over A, O1T, O20, trace B. I pull the trace right away, trace AB, O1T, O20, psi, AB at temperature beta, psi AB at temperature beta. Now this is a complete trace, so I can rearrange these guys by the cyclicity of the trace to obtain psi beta O1T O20 psi beta. So we already know how to get these guys by an imaginary time evolution, but we can also write this guy, if we go into the Heisenberg picture, as psi beta e2 plus IHT O1 e2 minus IHT O2 psi beta. So if I call this guy phi beta, then this thing here is nothing but phi beta taken to a real time t. So added to the imaginary time evolution, I put on a real time evolution, then I get my operators O1, O2, no, the operator O2 has already disappeared, sorry. The operator O1 survives, and on the left hand side I get the time evolved state psi beta up to time t. So the 2.2 time expectation value has been reduced to a single site expectation value between two different states. Okay, and then I can simply say, well, this is S plus and this is S minus, and I'm all the way to structure factors. Now, what you then can do is, once you have these guys, so what you would get here is like the correlator S plus, S minus, sort of like at times t, and site differences x, the distance between the location of 1 and 2, then you would get from that, you would get a structure function s plus minus of k and omega at some temperature beta by, and I omit all normalizations. This is not the problem here. I Fourier transform that e to I omega t. I do a sum over all sides, e to minus I k x n, and then I have this s plus n at times 0, s minus 0, 0, which is what I had up here. So all this, sort of like what you do here precisely, from where to where you integrate minus infinity to plus infinity or 0 only, depends on which of the functions of the whole zoo of structure functions, green functions, whatever you want to have. But the decisive point is you have this guy here and you have to Fourier transform it twice. Now, the Fourier transform in real space is not such a big problem. If you do open boundary conditions, of course, a problem arises once these guys get close to the end. But DMRG is quite powerful in doing large systems. So you can avoid it by doing a really large system or do something smart about boundary conditions. But the real problem, which I want to focus on, the one that really kills you, is this guy here. Because if you are not able to get very long time data here, you will get, first of all, you will get a bad resolution in frequency. And the second thing is, due to this Nyquist theorem, you will get aliasing, which means that the missing spectral information is simply folded into the spectrum which you calculate at places which you do not really fully control.
You don't need long time for it. You need the high resolution time for Nyquist.
Yeah, but if you don't have sort of like long times here, the resolution. Okay, I mean.
Nyquist is about sampling in time.
But you will still miss, perhaps then I've misexpressed and we should discuss it because I'm running a bit short in time, but you will definitely lose information. I may have not expressed it very well here. But anyways, if the times are limited, the spectral functions look totally awful. And the problem is, Adrian probably discussed that, the problem with time-dependent methods is that entanglement, while time evolution goes on, grows linearly in time in such systems. Or not as badly, but it grows. And in the worst case, where it grows linearly in time, the number of states you have to keep, or the matrix dimensions you need, will grow up exponentially. If it grows only, say, logarithmically in time, you will still have polynomial growth. Whatever happens, you hit a hard wall, and the wall we found was that the times we could reach without being too choosy about the numerics were some small factor alpha times beta. Beta being the inverse temperature. So, I mean, if we really push our numerical resources, perhaps we get 5 times beta or something. If you do a MATLAB code, you will get, say, beta. The problem is with the resources growing exponentially, even putting a much, much bigger computer will not get you that much further. So we did not bother too much about that, but the question was, can we get time t much, much bigger than the inverse temperature in order to get really nice spectral functions. If you look at the paper which I put into the lecture notes, Bartel, myself, and Steve White, where we show the best we can do with sort of like the raw results, and then the best we can do with the technique. I will explain in a second. You will see that it's really worthwhile doing something about it. Okay. And the way out is one which works both at 0 and at finite temperature, but I would say finite temperature, because it introduces natural damping into everything, is the best place to apply the technique, which I will explain in a second. And it's so simple that I can only encourage you to use it, because independent of which time-dependent method you use, you can simply improve your results without making too much of an effort, as long as you're looking at something like spectral functions. It does not work arbitrarily, as we will see in a second. And this would be sort of like the panacea for all the problems, but it's not. But for some important ones, it is. And this thing is called linear prediction. And this looks so simple that you could first not imagine that it gives any meaningful result. So let's take the time t, and I now have data points xn plus, and so on and so forth at different times, at, for example, time tn equals n times delta t or something like that. Getting these very dense is not really a problem in DMRG, it's just that at some point we will hit our famous exponential ball. And assume that this guy here is xn. And the question is, can we, from these guys, make a prediction what xn plus 1 and so on and so forth will be? Can we look into the future? And indeed, there's an ansatz, which is called linear prediction. Xn tilde is minus some I equals 1 to p. P is a number which is between 10 and 20 in numerical practice. And I take the data points before it, 1 time step back, 2 time steps, and so on and so forth, up to p times steps back. And I say that the next point in time is a linear combination of these older points in time. Okay, and this ansatz, of course, is very simple, and you may wonder whether it's any useful. So in order to actually make use of it, you have to determine these AIs. And so what we usually do is, this is the time up to which we could observe. And then we take a time t fit, which in practice we take usually to be t observed over 2, which is just to avoid any sort of like short time specific behavior which may affect negatively what is predicted about the long time behavior. But interestingly enough, shifting around the t fit, we did not find to affect our results very much. That's of course something you should do. If your prediction results depend strongly on how you place t fit, then you're in a problem and should not apply this method. So how do we do this? From data points we know, we can write a linear least square function. I have all the data points which are here in omega. Omega is this set of data points which I have here. I take the prediction xn and compare it to the true data I have obtained. And of course, so this is prediction, and this is actual. And then of course I want to minimize that with respect to this set AI. Well, if you do that, what you get is you get the following equation. Vector A is minus vector R. It's a P times P matrix, which you have here as R. The A's are of course the A1 to AP. The R is a matrix Rij, and the vector R is R1 to Rp, and we have to define these guys. Rij is the sum over all points for which we try this fitting, and then it's xn minus j star xn minus I, and the Rj is sum over all the data points where you try to fit xn minus j star xn. So this of course is trivially solved by A is minus R1 R. Let me remark right away, if you do that, you might have trouble in getting the method to work, because it turns out that this matrix will usually be very close to singular. What helps and what we found totally sufficient in numerical practice is to choose R It's mentioned in the papers, but it's always mentioned in a slightly, well, it's some footnote or whatever. We add a diagonal epsilon, and the epsilon we found to be good is something like 10 to minus 4, 10 to minus 5. Actually, what you can do is, how we determine the smallest epsilon that does it. I mean, if you make it big, you swamp out all the information. The smallest epsilon that works, we found in numerical practice in the following way. We calculated these A's for various values of K. I mean, we are calculating, sort of like we are focusing here, of course, on data points for various points in time for a specific K. So we do that for many different Ks, and assuming that there's a continuity in the physical problem, you would expect that these A's will not change much with K. So you should expect, if you plot these A1s to AP versus K, you should get something like a band structure, like Andy Millis showed you, or spaghetti-like structure. And what you will get in practice is you will get something like this, and then suddenly a huge jump, and it looks all very weird. And then when you turn up the epsilon, you will see that these jumps go away, and once the whole thing is smooth, you're done. So that works extremely well in practice. So when and why does this prediction approach actually work? Let's consider a Green's function, g of k and omega, which has the structure 1 over omega minus epsilon k minus the self-energy k omega. And there may be some plus or minus I etas around, but I don't care about those at the moment. The decisive point is the behavior of this guy is determined by the pole structure. And the pole structure in condensed matter physics is usually that these sigmas don't have infinitely many poles, but very often a very simple pole structure or one pole that sort of like dominates all the other contributions that show up. So let's assume we have a single pole in the whole thing. So meaning that we have a point where sigma of k and omega is omega minus epsilon k, so the whole thing diverges, and if that pole sits at omega 1 minus I eta 1, if you then do the Fourier transform from gk omega back to gkt, what you will get is, by the residual calculus, we'll get something like C1. C1 is the weight of the pole times E minus I omega 1t minus eta 1t. You will not normally get such simple structure if, for example, you said, well, I do that in real space. This simple structure depends on the fact that you have already gone to momentum space. So here really at this point, the very specific structure of a Green's function enters. Because if that were not the case, you could say, well, I can now take for this ansatz to work any physical quantity, anything will be fine. But the simplicity of the pole structure really usually holds in condensed matter physics for g and k and omega. And then g of k and t gets a simple structure in real time. So if you now compare that, okay, if you have multiple poles, what you would get is, of course, the sum of ci e to minus I omega it minus eta it. So this whole thing would generalize for multiple poles. And what you can work out, and it's on page number 12 in the handout, and I will rather just mention the statement, is if you iterate this prediction here, I mean, here you predicted by one time step. You started at n minus 1 and earlier times to get xn. But once you have predicted that one, you can go to xn plus 1 plus 2 and so on and so forth. And if you work that out, as described on page 12, what you will find is that if you predict m steps into the future, the result will be a superposition of I equals 1 to t Ci alpha I to the power of m, and alpha I is a number, a complex number less or equal to 1. Typically for finite temperature it should always be less than 1. Then it's omega I t minus beta I t. Which shows that the prediction structure that you get from this linear ansatz matches exactly the form that a Green's function has in momentum and real-time representation. And this is where the power of this prediction method comes from. Because I wanted to do the Blackboard only, look at the papers, but I mean a statement I can give you is that the range of time to which we could get was typically a factor of 10 to 20 more than the times we could actually reach by numerical procedure. For simple examples like the transverse Ising model where you can work out everything by hand, we could really check that these results were stuff like our raw data was up to a time of 10 in inverse hoppings, or 20, that we could easily do 200, and it was extremely accurate. For the spin 1/2 chain, which has a much more complicated pole structure because of the spin-on continuum, which is a much harder test case than a transverse Ising model, which has just one pole essentially. The agreement, sort of like with other methods, it's hard to do that at finite temperature because there was not anything really good around. There's Monte Carlo in imaginary time, which we've continued to real time, wiggles around our curve. If we take our data to imaginary time, it lies on the Monte Carlo data to 10 to minus 4 or 5 accuracy. So the problem is certainly again one of analytic continuation of the Monte Carlo method. And if we take it to the 0 temperature limit, the high beta with the problems that may occur, but I mean, I think it was beta 50 or something like that, which we then took to be beta equals infinity, and then we compare to the beta ansatz, a 0 temperature solution. There were only minuscule deviations, and the point is the beta ansatz people, while it's an exact ansatz, cannot evaluate the spectral function exactly. They only capture about 98% of the spectral weight. So given that we have extrapolated all our results in the number of states and whatsoever, I would be very confident that the remaining discrepancies are entirely due to the problem of beta ansatz, of adding everything together. So my message is that if you're really interested in spectral function and Green's functions, this prediction method at finite temperature is for the very small numerical input you have to do. You just take data which you have anyways, and then you calculate these matrices and do that, and you have to play around a little bit with making it stable. So the numerical effort is 0. And you get an order of magnitude in accuracy more. So I would really recommend that method. The other method I would like to recommend, not for that, but for going to extremely low temperatures, extremely high beta, the METS method you already heard about. I cannot cover it today, but you had the talk already, and I wrote something in my lecture notes, but which however closely follows the paper by Miles Downmeyer. But so if you don't want to read the entire paper, go for the few pages, and that's what I wanted to cover today with you. Thank you very much. Yes?
So what is the merits of this method, I mean, linear prediction in real time, and say, finding the...
Sorry, I still have something from the flight in my ears. Keep it louder.
So another method that comes to my mind is finding all the correlation functions at imaginary time, so you have to just go from 0 to just your beta,
yes,
to 1 time, and then finding everything, finding the whatsoever frequency components of the response function, and then
do analytic continuation. Well, analytic continuation is one of the nastiest procedures I know. Because, I mean, just in the example we discussed in our paper where we take the spin 1/2 chain, the agreement between our method and Monte Carlo raw data is so extremely good that I would say for all practical purposes the Monte Carlo data is exact. But when I then at Matsubara's and everything you described, and then I do the analytic continuation, and then depending on which of the various methods you use, it wiggles one way or another around the curve we calculate directly. So I feel all these continuation methods have their merits, and they are certainly not wrong. It's not like that they are totally off into the nowhere, but they are non-monotonicities, which in our curve are totally sort of like monotonous and stuff like that. So you really feel of course, if you have Monte Carlo and are happy with it, why not do analytic continuation? It's not sort of like totally obnoxious. But if you have time-dependent DMRG at hand, like from Alps or whatever, then sort of like doing that is minuscule effort to get really high quality data. So it's really a question of sort of like input-output relationship of times of work you invest in the whole thing, and there, this has its merits.
The reason I'm asking this is because propagation in imaginary time has less error than doing real-time DMRG, right?
Yes, but sort of like I would say the fact that you get sort of like that imaginary time evolution is sort of more stable than a real-time evolution is sort of like not weighed. Sort of like is outweighed by the problems of analytic continuation. That at least would be our experience at the moment. Yes?
So can this purification technique be used for other evolution? I was thinking of the dissipative evolution.
For dissipative evolution, it depends on which approach you want to take. If there for dissipative evolution, there is one way which basically writes down super operators, does density operators right away. I think you can combine that. The question is just sort of like how you would, whether you can sort of like translate it one-to-one. I've not really thought about that, but I would not see any real problem. The approach I would personally favor nowadays for dissipative calculations is one that takes standard DMRG calculation and combines it with a quantum jump approach. Unfortunately, we won't have time to discuss this here. Yeah, perhaps one thing which I should announce while answering your question, I hope next week I will have something on the web which basically is a big nuts and bolts review on how you to set up all these things, including these indices. That was an invited review, which is almost finished. I didn't get it done up to here. There I describe also this dissipative quantum jump approach because it's sort of like very powerful. And there definitely you can say whether you do it with a purified state or a sort of like true state, it wouldn't really matter. I think you can combine that. Whether it's numerically still powerful, I cannot judge without having tried it. But I see no a priori reason why not.
There have been calculations done, this dissipative approach with superoperators, as you say. So you can imagine.
Yeah, I know with the Michael Schollwoeck and Giffrey, but I mean sort of like that was at sort of like not combining it with finite temperature, if I remember correctly. Because I was thinking exactly about that paper when I was giving. Yeah, but the papers you would like to look at, if you're interested in that question, is one by Giffrey Vidal and Michael Schollwoeck, and another one which is by Frank Ignacio Frustrate and Garcia Ripoll, which does it in the matrix product state, and the dissipative quantum jump is by Andrew Daly and co-workers from 2009. It's all in that stuff I will have on the web next week, hopefully. So I would refer you to that. And then you would have to see how to combine all these things. More questions? Yes.
I just wanted to know the definition of this cost function that you're trying to minimize over. Is there any particular reason why all the weights are the same, or is there some?
This was just for the purpose of the lecture here. You can, of course, if you have the feeling that the quality of your results deteriorates over the time you're evolving, you would divide it by WN or something, which would introduce weights. The way we calculated it was that we kept the precision constant and went up with the number of states in the calculation. Then sort of like the weight function doesn't make that much sense. And we played around a little bit with it. And in the end, what we loved about this method was that there are a few fiddling parameters like the weights, like where you start the fit time, how many fit parameters you take, and unless you do something totally outrageous, the results were extremely stable under varying these parameters. The only one that was really tricky was to find this epsilon that makes this inversion stable. That was the one where we really had to play around with until we understood properly how this works. And this analyzing this spaghetti structure was really the way to do it, because then you have a visual inspection and you can do this inversion 1,000 times in 1 second and produce all these plots and it jumps into your face how all these jumps go away. That's very neat. Okay, so that was it for today then.